It's my truly pleasure to be here to have some talk in Quebec, such a wonderful, beautiful, and historic city of Canada. This year, marks the 100th anniversary of the birth of quantum technologies. Quantum technologies like quantum computing, quantum communications, and quantum sensing are emerging technology fields that are expected to make a huge impact on the future society. Right now, these technologies are advancing rapidly, and we are in a stage where their real-world applications are being actively explored. Today, I'd like to share some of Toshiba's initiatives as well as technologies in decentralized energy as well as quantum technology, hoping my talk give some insight into how quantum technologies could help shape the future of energy. My talk will follow with shown contents. First, I want to start briefly introducing my company, Toshiba. Our long-term philosophy is committed to people, committed to the future. Under the philosophy, we strive to build the infrastructure that everyone can enjoy and make a society connected by the data. As society stabilizes, we shift our focus towards the concerns of tomorrow, which include the well-being of our children and the sustainability of people and the planet. It is our responsibility to work towards carbon neutrality and the carbon economy under our philosophy. This slide highlights key figures of the company. Toshiba was founded in 1875, so this year we are celebrating 150th anniversary of the company, long before quantum technology even existed. Annual sales is $3.5 trillion, approximately 23 billion US dollars. Some of you may know Toshiba, our company for laptops and TVs, but we have spun off those businesses. Today, we are focusing on energy, social infrastructures, electronic devices, and digital solutions. You can see our broader products and solution lineups in each business segment. As I will explain later, now we start the business with quantum communication and a quantum-inspired computer. Everyone agrees the power of digital. Data are becoming increasingly important now. As a digital economy evolves, new social value will emerge with the companies connecting across the industry boundaries. To address these changes, Toshiba has defined a strategy built on DE, DX, and QX. The first stage of the strategy is digital evolution, DE, which focusing on the enhancing existing service and creating a recurring business with using the power of digital. Next comes to digital transformation, where we build platforms for services based on DE. Ultimately, we aim for quantum transformation, a quantum-driven world where platforms connected across industries and the digitized data is secured by quantum technology. Then I will show you a bit about energy supply and AI trend in Japan. Although many countries have a vision and roadmaps for achieving carbon neutrality by 2050 or earlier, their current situation and the path to get there vary widely. Japan's energy policy follows the 3S plus 3E, principle for energy supply and carbon neutrality. S stands for sustainability, three E's are energy security, economic efficiency, and the environment. To achieve carbon neutrality in Japan, where only a few nuclear plants have restarted after the 2011 Great East Japan earthquake, land for PV or wind farms is limited. We have heavy typhoons frequently, and the electricity demand is surging due to AI. We must overcome several challenges. Those are, as you can see, A, effectively utilize renewable energy, B, develop and deploy high-efficiency, low-cost renewable technologies, C, promote energy saving and optimize social activities, D, curb the growing power consumption of AI. The graph at the bottom right shows electricity demand by data center in Japan that is projected to exceed 40 terawatt hour by 2032, more than 4% of the current total energy consumption in Japan. To address the growing electricity demand from the data centers, the government of Japan and the industry have launched an initiative called the Watt-Bit Public-Private Consortia. Interestingly, their policy emphasizes R&D on all photonic networks and enabling a demand response for data centers. Given the constraints on grid power supply and the need to reduce the carbon emissions, we plan to build decentralized data centers with demand response capabilities and to implement workload shifting across multiple sites. In other words, we are looking at moving generative AI training workloads between the regions based on the available power capacity, which fluctuates with weather conditions. That's where APN, all photonic networks, becomes critical, enabling massive data transfers between the data centers while minimizing latency and the power consumption of data transmission. So now I want to explain about the Toshiba solution for those challenges. Again, here I'm showing challenges here. To achieve A through D, we obviously need to leverage data from society and the energy systems. And that data must be safeguarded against the growing risk of cyber attacks. Now, let's take a look how Toshiba solutions, along with the quantum technologies, can help overcome these challenges. Number one, I will explain about our first solution, VPP, virtual power plant, that is working on highly accurate prediction for electricity demand and solar power generation. Both demand and solar output by region, depending on the weather and temperatures, To tackle this, Toshiba developed its own global weather simulator, producing larger and higher resolution data than standard forecast. We also created an advanced PV power prediction method that combined PV engineering models with AI-based equipment parameter estimation. These innovations earned Toshiba the Grand Prix in the global competitions for both prediction and methods. Accurate forecasting of the electricity demand and the renewable generation is a key to making a most efficient use of renewable energy. Yesterday, during a dinner or a tour to the Q-Scale, I was so surprised that many of you know our battery, SGIB. SGIB, with the lithium titanium oxide as an anode material, has unique advantages compared with the standard lithium-ion battery. As entirely safe, never flammable, rapid charging and higher output density per volume, long cycle life over 10,000 cycles, and low temperature operation, about minus 30 degrees. SCIB batteries are now being adopted in logistics vans and EV buses in several countries. In contrast, conventional lithium-ion batteries equipped vans require several hours to charge, forcing delivery companies to maintain 2 or 3 times more vehicles to cover routes while others are charging. By comparison, a van equipped with our SCIV can be fully charged in about 10 minutes, roughly the time it takes to load packages at the delivery center, allowing a single vehicle to handle last 1 mile deliveries efficiently. This frequent rapid charging also makes it possible to use a smaller battery system on vehicle, reducing the weight and improving the energy efficiency of the vehicles or vans. Our carbon dioxide tandem PV technology offers a high-efficiency, low-cost solutions aimed at e-mobility as well. Toshiba's unique transparent carbon dioxide PV cell has a different band gap from the silicon, so by pairing it with a standard silicon cell in a tandem structure, we can achieve solar cell efficiency of over 30%. We are also working on the PEM-type electrolysis on the right side. PEM electrolysis is technologies too great for producing hydrogen from fluctuating renewable energies. But it has a drawback. It requires a large amount of iridium, very rare and much, much expensive than platinum. To address this, Toshiba's research teams developed a midfield-like coating structure that can reduce iridium usage to just 1/10 while maintaining efficiency. Right now, we are collaborating with a Belgian company, Becal, to manufacture the MEAs for hydrogen electrolyzers targeting a European market. Gallium nitride and silicon carbide power electronics are also in high demand to boost AI data center efficiency and shrink the power supply unit for data AI servers. Our second generation gallium nitride power chips, combined with our own drive control IC, can provide a better efficiency and cut the size of power unit by about 60% compared to standard silicon power chips. Now, with showing Toshiba's quantum activities and technologies, I'd like to consider how quantum technology could contribute resolving the challenges previously mentioned. Let's start with the quantum computers. Quantum computers can be classified into 2 types: gate-type computers and Ising-type ones. Gate-type quantum computers, which are expected as a multi-purpose ones, are studied and developed by universities and several companies like Google and IBM. On the other hand, Ising-type machine, which becomes popular with the D-wave solution, a specialized machine for solving large-scale combinatorial problems. Ising-type computer is further divided into 2 categories: quantum computer like a D-wave solution and quantum-inspired ones. Quantum-inspired computer is one which can be implemented with a legacy digital computer architecture, and several algorithms and machines have been developed by industry, mainly in Japan. Toshiba also invented unique algorithm for quantum-inspired machine called simulated verification machine SBM in short, which is inspired by our theoretical quantum computer research. Combinatorial optimization problems appear in various social issues, such as portfolio strategy for financing trading, optimal pathfinding in logistics, traffic control, optimal scheduling or assignment in industry, material design, and drug discovery. With increased number of elements, the size of problem becomes exponentially large and cannot be solved with a digital computer. Those combinatorial optimization problems, however, can once be expressed as an Ising problem. Their solution can be obtained quickly with the Ising machines, either quantum computers or quantum-inspired ones. We, Toshiba, have worked with our customers and partners to apply our SBM to protein design or drug discovery, financial trading, optimizing for logistics routes, etc. And here, I want to show you our unique trial SBM application to on-vehicle automotive driving. Collaborating with the company Denso, we implemented the SBM system with vehicle-mountable 2 FPGA boards. One is for AI processing, and the other is for SBM. We achieved the system throughput of 20 frames per second and the SBM unique functions. That is, flexible matching or tracking moving objects like pedestrians through multiple long-term occlusion events. We also found the SBM can prove accuracy of SLAM to generate a surrounding map so that we are boosting the development to implement quantum system on the vehicle shortly. We used SBM to tackle a simple optimization problem in a virtual power plant, set up with the multiple batteries and the power sources. As mentioned earlier, compared to conventional algorithms, the SBM can find better solutions to large-scale combinatorial optimization problems in much less time. To test SBM's performance, we applied it to a scenario of a VPP system with 1,000 batteries and power sources. Under a 1-second computation limit, SBM found solutions with cost 56.4% lower than those from conventional algorithms. To use SBM, the problem needs to be formulated as an Ising model. Now we are working on applying the approach to more complex optimization challenges like power grid control and stabilizations. Quantum-inspired systems are also being used in material design. For example, the University of Toronto and Fujitsu in Japan combined Fujitsu's quantum-inspired machine with a cluster expansion model to discover a new family of catalysts for the acid-oxygen evolution reactions. While quantum-inspired computers or machines aren't real quantum systems, they have the potential to make a real impact on the future of energy in many ways. Back on the track to gate-based quantum computers, this figure shows a recent roadmap of the number of physical qubits where italic number indicates logical qubits after error correction. Many enterprises, startups, and universities are now racing to increase the number of logical qubits to build fault-tolerant quantum machines. This shift comes as it's become clear that NISQ machines can hardly tackle real-world problems because of their limited circuit depths or calculation depths. Along the various approaches to implemented quantum circuits, superconductive and neutral atom technologies seem to stand out at the moment. Both are making progress in scaling logical circuits, qubits, thanks to their low gate noise compared to the other methods. In Toshiba, in the field of torrent quantum systems, Toshiba is focusing on R&D on the key technologies to achieve low noise, high-speed qubit gate operations using our invention called double transmon coupler. Compared to conventional coupler technology with a single superconductive transmon qubit, which Google and IBM are now doing research on, Toshiba's double transmon coupler delivers three major advantages at the same time. They are the ability to completely switch off the coupling, strong coupling for the fast gate operations, and the final one is compatibility with the highly detuned qubits. We are currently working with RIKEN to design and fabricate double transmon coupler devices and have achieved world-class 2-qubit gate fidelity of 99.90%. Believing that DTC will become a core technology for fault-tolerant superconductive computers, we are pushing towards a fidelity of 49%. Then I'd like to move on to quantum communication technology of ours. Today's communications are generally secure because it takes a huge amount of computation to break encryption. However, when the large-scale quantum computers appear and their immense increases in computational power become available, the encryption that now protects the communications security will be easily broken. Once that can be done, it is possible to intercept, decrypt, and exploit communication information. Even if the data cannot be decrypted now, there is a risk of data harvesting, where encrypted data is collected now for decryption after large-scale quantum computers become available. So in order to deal with those threats, quantum key distribution, QKD in short, provides a secure means for generating and distributing secret keys between the two pairs on the optical network. It relies on encoding bit of the key upon the qubit state of a single photon transmitted through an optical fiber or over the air. As many attempt to read photons alters their encoding, this allows the secrecy of each key to be tested and guaranteed. Unlike other existing security solutions based on math, QKD is secure from all kinds of future advances in mathematics and computing, including the data processing power of quantum computers. Toshiba has done research on QKD for about 30 years now and introduced two types of quantum key distribution platforms in 2020 with our native technologies. First is a platform for long-distance applications that maximize the key generation rate and the distance of communicating parties for key delivery. Second is an innovative multiplexing platform that allows user data as well as quantum signals to be transmitted on the same fiber, eliminating their need for costly dedicated fiber infrastructure for key delivery. We are now in Quebec, a city where QKD field trials are actively taking place. Right now, Many countries, including, of course, Canada, the United States, the UK, EU, Japan, and others, are running field trials of QKD in the cities. And Toshiba is supplying our commercial system to many of them. In Paris, France, Orange and Toshiba announced a commercial key delivery service using QKD earlier this year. Let me share our example of recent R&D on QKD. Current QKD systems are built with expensive, high-precision optical components. However, at Toshiba, we've already developed our next-generation QKD systems using silicon photonics circuits, and we plan to begin field trials in UK early next year. With this smaller and lower-cost QKD technology, we believe usage of QKD would be expanded globally. Recently, Purdue University and Toshiba announced demonstration of quantum secure communications applied to Purdue's nuclear research reactor system. This is actually the first time QKD has been demonstrated in a real-world nuclear facility. The project took place at the PUR-1, which was Purdue's fully digital research reactor. Toshiba's long-distance QKD system was integrated into the reactor's control network, enabling real-time encryption and decryption of sensitive reactor signals. They achieved the secure data transmission of a distance up to 140 kilometers using both one-time part encryption and AES-256 encryption methods. This demonstration is a big step for the practical use of quantum cryptography in the energy sector. As we see, quantum computing and quantum communications technologies are advancing rapidly, and we are starting to find real-world applications emerge. Just like Canada's QIC, Japan launched an organization called QStar in 2021 to promote a business use of quantum technologies. QStar already has 137 member companies and the universities, and what's unique is that many of them are end-user companies, not just tech companies. The group is actively working on exploring quantum applications for many sectors in financing and energy sectors, logistics, and quantum talents development now. As conclude, I would like to say quantum technology is no longer a dream, no longer our future technologies. Instead, it is becoming a reality, and we have various opportunities where quantum technologies could be applied in decentralized energy sectors. We, Toshiba, is striving in the area, hopefully with you, and create a super fast and secure quantum economy. Thank you very much for your attention.